Welcome everyone to the week 11 of the complex analysis course. We'll, as usual, discuss maybe summary of the week, what we have learned in this week, and then we'll solve some exercise problems. Right. In this week, I would like to request please subscribe my channel and like my videos if you like. Okay, so what happened this week? We first started with defining branch of logarithm. So by branch of logarithm, what we mean is this. Uh, so we can start from here. By a branch of logarithm, uh, we mean what? We mean a map from a branch of logarithm with domain omega is in this way. We mean some f from omega to c such that exponential of fz, this becomes identity for every z inside omega. F is a holomorphic function. Then we say, so if it is, okay, in general, it is defined to be some continuous function like this. We say it is a branch of logarithm. It may not be holomorphic, of course, but we are trying to find out branches of logarithm which are holomorphic in the given domain. Okay, so for that, so in this week we also discussed if such a branch of logarithm exists, let's say it is holomorphic. In that case, if it exists, then what is f prime z? We check this using some chain rule of derivatives 1 by z, right? For every z inside omega. If branch of logarithm, which is, let's say I'm taking now holomorphic. So if f is holomorphic, then in that given domain, its derivative will be 1 by z. So we see that there will be problem. So because exponential is mapped from C to C star, right? It is also not injective. So exponential is not one map. So and f is means branch of logarithm which we are searching is inverse of exponential in some sense. So here we see that once exponential is not 1, we cannot get a branch of logarithm from C star to C, means complete inverse of exponential, right? So the problem is, since exponential function is not injective, we don't expect and exponential map is not injective. Okay, so we have to fix our domain and codomain. Exponential map from C to C minus 0. This map is not injective. You know why? Because e power z and e power z plus 2 pi I something, you add them, you get same value. So it is not injective. C minus 0, f from C minus 0 to C, such branch of logarithm do not exist. Okay, because we want to take inverse of some function, and this function which we are defining on the domain c minus 0, it does not work. So we have to restrict our domain first of all. To get an inverse, we restrict our domains. So we'll see what kind of domains we have to restrict them injective such that, okay, such branch do not exist. Right. Many more other things like some example were given branch of square root. What is that? So usually, there are two ways to define a square root. One is for any given number, positive number, of course, because a square map is taking all real values to positive real values. So square roots will be given in two different manners. Either it is plus a square root of that given number or minus of that. So we can define in this way uh, in the domain. Let's say 0 to infinity is our domain for defining branch. We fix our domain, subpart of domains where we define uh, plus a square root of given number or minus of a square root of that number. In this sense, if we define in a given, let's say 0 to infinity, we define plus a square root somewhere, minus square root somewhere else, it will be discontinuous, but it will be one of the branch because we are in the domain, we are fixing particularly where is this number going. Okay, right. And for every given number, we are defining a function. Either it is plus a square root or minus square root, doesn't matter, but we are defining that because we had two choices and we fixed one choice. Same here, like e power z and e power z plus 2 pi I. These two are numbers going to same. So we are going to define log of z. Log of z, if you define, what happens? If you get a set, so log of z will be some big set. So as big as natural number is. So there's this definition. We'll see this. Uh, I have some notes of the classroom. So one thing is that whenever, so this is one of the theorem maybe, when omega is simply connected, and 0 do not belongs to does not belongs to omega, then there exists a branch of logarithm. There exists f from omega to c such that e exponential of f of z, this becomes z for every z belonging to omega. Okay, so such a branch of logarithm exists when omega is simply connected and 0 does not belong to given domain. Fine. So simply look at this domain. So this was not satisfying our condition. 0 does not belongs to here, so it is not simply connected. Okay. It is not simply connected. We don't need to check. Okay, fine. Now, how is so there are if we have two different branches in given same domain omega, so let f g from omega to c be branch of logarithms. But wait, what I have, what I want to tell is that it is not uniquely defined. We have many choices for defining f and g. So what is difference between f and g, right? That is what we are going to see. If f and g are branch of logarithm, then e power f and e power fz is same as e power gz, right? And these two are equal to z because they're for every z inside given domain omega. Now, if you take these two quantities one side, then we get e power f minus g of z is equal to 1. And this implies, so when it is a constant, what happens? F minus g, right? F minus g of z, this function is constant. So there may be so it is constant of what format? Because it could be 0, it could be 2 pi I, to 4 pi I, something like that. Because we are going to get e power some constant. That constant is equal to 1. Means e power that constant is 1. So it is f minus constant of the form 2 pi I k. 2 I pi k, whatever. So it is a constant of this format, right? And now that so in this case uniquely defined because f minus is a constant, and so this is constant of so k is uniquely defined by what is f minus c. If you check at one value, it will show you what is k. Okay, so uh, hence between two, after that, when we know branch of rhythm, we also saw branch of z power n's because nth roots, branch of nth roots, like explicitly saying, just like a square root, we have two choices for a given number. What will be the square root? For nth root of unity, sorry, nth root function, we have n choices. So we have to fix our choices in a given domain, right? So that is what is discussed in the same lecture, maybe. So in the next lecture, we saw about Schwarz lemma. What is Schwarz lemma? We'll write here Schwarz lemma. What is that lemma? If we for unit is okay for a map of this moment, f from t to d, unit disk to unit disk, which is holomorphic. Holomorphic with extra condition. F d to d holomorphic such that f of 0 is 0. Then what we have two claims. First is that f of z is always less than, this modulus is less than or equal to mod of z. And the second thing is f prime at 0, this modulus is less than or equal to 1. And there was one more thing. So moreover, what happens? Extra condition is that if equality happens in the second. If f prime at 0, this modulus is exactly equal to 1, or fz is equal to the modulus of fz is equal to modulus of z for some z in D. We have there exists lambda in boundary of D. In boundary of D, this means modulus of lambda is equal to 1, right? Lambda lies in unit circle, such that f of z is nothing but lambda of z. Okay, so this is what Schwarz lemma was. So there's little mistake for some z in D star. D star means D minus 0, because f of 0 is equal to 0 we have already taken. So modulus for them are equal. 0 has modulus 0 and f0 has modulus 0, because f0 is equal to. So other than 0, if we have some point where f modulus of fz is equal to z modulus of z, then this happens that fz is equal to nothing but lambda z, and it is rotation, right? Right. So after Schwarz lemma, we are not going to see the proof. So we have talked about, we have seen this about automorphism of unit disks, right? So one of the thing which is to remember, we have solved many times, what is this function. So this phi of a, which is a minus z divided by 1 minus a bar z. This is an automorphism of unit disk. An automorphism of unit disk. Now, so one thing we concluded at the end of second lecture or third maybe this week, that what are all automorphism of unit disk, right? So do we want to see the proof of that? Because in the proof we have used Schwarz lemma. I don't know how many times, but we have used. So one thing is that its inverse is, this is self-inverse, or phi of a has inverse phi of minus a. So we can solve for it. So phi of a sends a to 0. Phi of minus a sends 0 to a. So they are inverse of each other. Okay, right. So phi of a inverse, this function is equal to phi of minus a. And if we have some automorphism, so the question is, for D to D a map, which is holomorphic. So one question we had discussed, what is modulus of f primes in whole unit is when f is map from D to D, sending alpha to beta. So this was also discussed, and we have found that f prime of z or f prime of alpha, this modulus is 1 minus beta mod beta square divided by 1 minus alpha square. It's just we are just using Schwarz lemma where f of alpha is equal to beta, and f is always mapped from D to D, so nothing has been in extra hypothesis. When f is from D to D holomorphic function, then f prime is bounded by this number, less than or equal to this. Okay, right. What more? So this here equality happens in the second scenario when fz is equal to lambda z, or f prime at 0 is equal to the modulus is 1, exactly 1. In those scenarios, this becomes equality. Right. So one of the last theorem. Okay, we have some extra thing, Friedman-Lindelof method, which I have not gone through yet, but we'll see. Actually, not all of them, but some of them. F from D to D an automorphism, then there exists alpha and lambda in boundary, alpha inside and lambda in the boundary, such that f of z is equal to lambda into pi of a. Okay, so this way. The theorem is, let f from D to D be an automorphism. Automorphism means it is holomorphic, its inverse exists, and inverse is also holomorphic. Automorphism. Then there exists alpha inside the unities and lambda inside boundary of unities, such that f of z is equal to lambda pi of alpha z. Right here again we had seen the proof of so using Schwarz lemma it follows directly. So, right, so Friedman-Lindelof method. So I have not gone through the whole method. Uh, I'm watching notes, so that I will. So if we have a vertical strip as our domain, and from the closure we have a holomorphic function, and modulus of f is bounded by some value b, then we have a relation between what is m here. I don't know what m is. M a into mb. I think we can leave it. Omega is bounded connected. Open local. It is standing for local maxima or local minima. I don't know. So we are leaving that part. Okay. Yeah, we are not going to discuss now. Uh, we let's see our exercise problems. I think we can even do without knowing what is Friedman-Lindelof method. but it is important. It is about relation between maxima uh, of given holomorphic function in the boundary, right? It attains its maxima in the boundary. So if we have infinite strip, so boundary contains two vertical lines. So what happens if we take maximum in left vertical line and maximum left in right vertical line? So there's some relation that we are not going to see. We'll solve some problem now. So let's see now problem, first problem. Omega B open connected subset of C. There always exists branch of complex logarithm holomorphic on omega. So we have seen this. So A option is incorrect. It is half. We can write reason because we can C minus 0 is open connected, but there does not exist any branch of logarithm. So the reason is already given in the class. If there exists f from C star to C such that so exp of f of z is equal to z, then f prime exists everywhere and it is given by 1 by z, right? So it has an antiderivative. Right? 1 by z has an antiderivative which is given by f, right? Then what is integral of d by z, sorry, 1 by z in unit circle? It is 2 pi I, which is non-zero. But when we say that it is having an antiderivative, for example, f is antiderivative in this scenario, f is an antiderivative of 1 by z, then it should be 0 by fundamental theorem of calculus or theorem of calculus, first fundamental, I think, right? In the second, I think it was kind of when all the integrals are 0 or all closed curves, then function is having antiderivative. But here in the first fundamental theorem, it says like this: for a closed curve, if function has antiderivative, then integral will be 0 over closed curve. So it is not the case. It is a contradiction. So for B, what we can say, there always exists a branch of logarithm on omega, which is a subset of C star, where the set C star is C minus 0. Again, the same logic follows as A. So subset of C star, what we can take? C star itself, there does not exist. Uh, taking omega is equal to C star. This is also improper subset. Okay, so this is wrong. In particular, for giving counter example for A part would be anything where 0 belongs to omega. Okay, in the B taking C star works or C part, there always exists a branch of complex logarithm holomorphic on omega, which is omega is subset of C star, means 0 does not belongs to omega. And when omega is simply connected. When omega is simply connected and 0 does not belong to there, in this scenario, we have seen the proof of uh, existence of branch of logarithm. So uh, there was this trick, I think, we were using because it is simply connected. So over any closed curve, integral vanishes or holomorphic function. Uh, no, for any closed curve integral, once integral vanishes, we get an antiderivative, right? Using Morera theorem, something like that. And once we have antiderivative, so that antiderivative is holomorphic, and we have seen once the function is holomorphic, it is holomorphic infinitely many times. So the actual function f is also holomorphic in this sense. Right. So 0 does not belongs to omega. This means 1 by z is holomorphic function in omega, right? Now omega is simply connected. So over any closed curve, what happens? Integral of 1 by z vanishes inside omega. So by using Morera theorem, 1 by z has antiderivative, and that antiderivative is what branch of logarithm is. Okay, so we have seen the proof in the lecture, the classroom lectures. So what is the trick here? 0 does not belongs to omega. This implies 1 by z is holomorphic. On omega, and since omega is simply connected, this implies integral of 1 by z dz is equal to 0 for every gamma, which is closed curve, in omega. This implies using Morera theorem now, Morera theorem, or I think second fundamental theorem, Morera theorem, 1 by z, right? We should write in some other thing. There exists f from omega to c such that f prime z, this is equal to 0 does not belong to omega. This implies 1 by z is holomorphic. Right. There was a, I was saying something else and writing something else. Sorry for that. 0 does not belong. So in this scenario, Morel theorem tells there exists some function f omega to c with this condition that f prime of z is equal to 1 by z. Now it has an antiderivative, right? So f prime, which is 1 by z, it is holomorphic. So f is also holomorphic, whose derivative is defined everywhere. So we get a branch of logarithm. This is what we were searching for, right? So this is true. Now, what about part D? Let omega belong subset of C star. This means 0 does not belong to omega. Have a branch of logarithm. Okay. So a branch of logarithm is defined on omega. Then every branch of logarithm continuous on omega is holomorphic. Right. What we have seen for the D part, we have seen that once f is, let f be one of the branch of logarithm, which is holomorphic. Any other continuous branch of logarithm, any other continuous branch of log is of on omega is of the form f minus or plus minus 2 k pi I, something like that. So for some fixed k, uh, or some fixed k. So what this means, f is holomorphic and this is constant function. Add or subtract doesn't matter. So constant function is also holomorphic. So f is holomorphic. So f plus some constant. Then the other functions, they're also holomorphic. This implies any other continuous branch of logarithm on omega, say g, say g, then of this form. Then this implies g is also holomorphic. G is also holomorphic. Right. So D is also true. Now we can take a second question. So for the second question, let's see what we are doing. Let f be holomorphic function on unit disk with 0 of order n, which is greater than or equal to 1, at the origin, such that modulus of f is bounded by 1. This means it sends unit disk to unit disk. Okay. Oh, no, unit disk to unit disk closure. They're not talking about closed disk or open unit disk, but we are assuming that they are closed unit disk. Okay. So for the timing, let's assume these are closed unit disk. Check the boxes corresponding to which true statements are given. So in the first option, they're saying that there exists Z naught in T such that f of Z naught is equal to, sorry, bigger than Z naught. Right? What we have seen in Schwarz lemma. So 0 of order n bigger than or equal to 1, order bigger than or equal to 1. This implies in particular f of 0 is equal to 0. So now just we use Schwarz lemma, and what we get, f of z is modulus, this modulus is less than, so we can write here in the downside what Schwarz lemma implies. F of 0 is equal to 0 and f from D to D is holomorphic. These two conditions together implies modulus of f of z. This is less than mod of z, or every z in D less than or equal to, sorry, and modulus of f prime 0, this is less than or equal to 1. Right? Now this is the incorrect statement, right? This is true for every z in D, that modulus of f is bounded by modulus of z. So we are using Schwarz lemma and we are done. Right. What about part B? For all z in D, we have modulus of f of z is bounded by modulus of z to the power n. So, do you remember the proof of Schwarz lemma? How, how was that proved? So, maybe similar proof will be here also. Let's see. There we had just f of 0 is equal to 0, a simple 0, right? But here we have 0 of order n at 0. This means f of z is of this form. But we are looking for part B. F of z is nothing but z to the power n into g of z. Such g is holomorphic such that g of 0 is not 0. All the zeros of f has been encountered in this function z to the power n. So g of 0 is not 0, and g is also, of course, holomorphic function. G holomorphic. On the okay, so modulus of f is bounded by 1 because they are sending unit disk to unit disk. What can we see from here? We have to show that uh, what is the relation between modulus of f and modulus of z to the power n. Okay. So let these of this form we already considered. So from here we have g of z is equal to f of z by z to the power n. What can we see from here? So this function does not vanishes at 0, right? So in a neighborhood at 0 or in a whole disk. So let me see the proof of Schwarz lemma, and the same proof I think works in this scenario also. It has removable singularity. Fz by z to the power n has a removable singularity at 0. So in a neighborhood of 0, this function g function is holomorphic. Now by maximum modulus principle, oh, fine. So the proof is like this. So we have a unit disk here. and we look for these smaller disks. Let's say this is small r radius. This is radius 1 unit circle. Then on D0R closure, we are using maximal modulus principle. Maximum modulus principle. We get G of Z, the supremum or maximum. Here we set say maximum because we are checking in closed sets. Maximum of Z belonging to D0R bar is equal to uh, not this exactly. We are taking mod here. So it's maximum over boundary Z belonging to del D0R bar of Fz by Z to the power n. Now Fz by Z to the power n is holomorphic. We have just seen few seconds ago that it has a removable singularity at 0. So what we get here, Fz is always bounded by 1 in the whole unit is. So it is less than or equal to 1. And what is Z to the power n? Z to the power on the boundary is always fixed. It is R to the power n. So when R tends to 1, when R tends to 1, then this maximum value, maximum of mod Gz, Z belonging to whole D01, okay, whole unit disk. So we can write this way. Maximum Z belongs to D. This is bounded by 1. This R tends to 1. 1 by R to the power n goes to 1. This implies that Fz by Z to the power n, this mod, is always bounded by 1 for every Z inside D. And this implies modulus of Fz is bounded by Z to the power n. So we get a proof for our case, right? The similar proof was given in Schwarz principle, Schwarz lemma. So that is why I had to go through the proof. I don't remember the proof right now, so it's good to go back to see them. We also find this pretty interesting. We are just using maximum modulus principle. So this is an important principle we had to remember because we are using again and again or various tricks here and there. So we saw this for part B, we have found our answer. This is correct. Now we are going to check part C. So in the Schwarz lemma, we also see we have seen the proof of first part. If we had this Fz is equal to Z into Gz, if we had simple pole, then the first inequality has been proved. A similar trick will work in our scenario. But there was one more thing to prove in Schwarz lemma, that a prime 0 has modulus less than or equal to 1. What is that? That is first in the Lorentz series expansion, this f prime 0 is first constant term in the Lorentz series expansion. Z into f prime 0, right? So similarly, what is first constant term? Sorry, first what is coefficient? First non-zero coefficient of Lorentz expansion in this scenario will be what? So fz can be having expression like because f is holomorphic, fz can be written as f of 0 plus z into f prime 0 plus and so on fn minus 1 at 0 z to the power n minus 1 by n minus 1 factorial plus fn 0 z to the power n by n factorial plus and so on. So we see here what is first non-zero coefficient. These terms are 0. Why these are 0? Because at 0 we have root of order n. Z to the power n will be our first degree in our Lorentz series expansion or Taylor series expansion in particular because f is holomorphic. So all these f of 0, f prime 0, f nth n minus 1th derivative, they are all 0. But nth derivative will be non-zero. And the first non-zero coefficient will be fn 0 by n factorial. So this modulus will be less than or equal to 1. And this will imply that fn 0, this modulus is less than or equal to n factorial. So this is what in our option is. And this is true. Now I have directly written why this modulus is less than or equal to 1. How can we see exactly what is happening here? Why the first non-zero coefficient is bounded by 1? So again, in the situation is same. There we were talking about first non-zero coefficient, which is f prime 0. Here it is nth. So what is the proof for that? So what is this value? F n. So we have one thing that fz by z to the power n means exactly gz. Okay, gz. Gz modulus of gz is bounded by the maximum value is 1 here. We have calculated in the B part. G of z, this modulus is always bounded by 1 for every z in T. What is G of 0? We can calculate from the previous thing. So G of z is what? F of z by z to the power n. This was our G of z. And which is also f nth derivative at 0 by n factorial. Now because z to the power n has been taken common outside, so we have n plus 1 here, 0 by n plus 1 factorial into z. Now we start from here. So this is constant term of g. So what is g of 0? G of 0 is exactly equal to f nth derivative at 0 by n factorial. When we take modulus of this, we are going to use a star. This is bounded by 1. This is from star. So this implies what we want to get. Okay. So we found the proof. G of 0 is exactly our f n derivative at 0 by n factorial, and that is having modulus less than or equal to 1. So we see the proof. We are happy. Now for part D, what we have to do? It is said that 1 by f of 1 by 2 is 1 by 2 power n. Then f of z is equal to c into z to the power n, where c is having modulus 1. How to do this? It seems that it is correct because the situation is almost similar in as in previous scenario in the Schwarz lemma. There we had that if f prime at 0, this part, if f prime has 0 has modulus exactly equal to 1, or for some point modulus of fz is equal to modulus of z, what happens to f? F is of the form lambda into z, where lambda is having modulus 1. So here, because it has n roots at 0, already we have seen this format that z to the power turns out to be one of the coefficient of the function f. So what is g? G is constant and it is lambda and having modulus exactly equal to 1, right? But we have to see the proof of this. Okay, we cannot leave it like that. So how can we do this? Let's think about this. So we have considered g of z is equal to fz divided by z to the power n. So now g do not have 0. Oh, what can we do? What if we take gz is equal to fz divided by z to the power n minus 1? Then it has simple 0 at 0. Also, this modulus is less than or equal to 1. It sends unit disk to unit disk. Then it is fine. Right. What I was thinking, I'm going to write it now. A function that satisfies the inequality, it is done. F of f of 1 by 2 is 1 by 2 power n. So g of 1 by 2 is equal to 1, right? D part, g of z is this is defined to be f of z by z to the power n. And it is mod of gz. We have seen that this is less than or equal to 1 because f of 1 by 2 is equal to 1 by 2 power n. This implies g of 1 by 2 is equal to 1, right? So G attains its maxima inside. You understand? G is a holomorphic function from unit disk to unit disk. So we got the proof. G is holomorphic map from D to D. D to D means we are always talking about closed unit disk here. So don't worry about that because their interior part goes to interior and boundary part goes to boundary. So we have attained a interior point where it attains maximum, right? At 1 by 2, what we are getting? G of 1 by 2 is equal to 1. What this implies? Open mapping theorem tells what? Or maximum modulus principle. Non-constant functions are uh, open maps or something like that. Holomorphic functions are open maps uh, if they are non-constant, of course. And in this case, it is not open around 1 by 2. If we take an open disk, it doesn't go to an open disk, right? Because 1 by 2 is going to 1, which is lying on the boundary, and there is no open disk at the boundary. So open mapping theorem or maximum modulus. Open mapping theorem. So the scene is this. We have our point is here, 1 by 2. And where is image? Image is going to 1 by 2 is going to 1 here. If we take any open disk around here, this should go to an open set, right? 1 by 2 should be interior point. Means interior point goes to interior point via F. This is contradiction. Fails. Because G is holomorphic. This is contradiction, hence G is a constant function. G is a constant map. This implies some constant, let's say G of Z is equal to C, right? Now what should be this constant? This constant should be exactly equal to 1, right? We also know what is that constant because once G is a constant function and it attains at 1 by 2 equal to 1, image is equal to 1, then this constant is equal to 1. So we are not thinking anything else now, right now. Now we are done, mostly done, because C of Z is equal f of Z by Z to the power n, which is equal to 1. This implies fz is exactly equal to Z to the power n. So that constant C is equal to 1. So here is that value. Okay. Here's this is the way we proved it. There may be some other way to prove it, but you understand the picture here because 1 by 2 was interior point and 1 is not interior point of unities. So open mapping theorem is failing. Our function, which is holomorphic, should be constant function because it attains one value 1. So the constant is exactly equal to 1. Now fz by z to the power n is 1, so fz is z to the power n, and the proof is done. Right. I hope you like this proof. This is true. Okay. Let's see other questions because we have, I think, 2 more questions to think about. I don't think we will use Fragman-Lindelof method, but it is important to look back. I have not gone through that, but I will suggest This is not the same function as in the classroom. Okay, because the function was given like this: a minus z divided by 1 minus a bar z. It sends unit disk to unit disk. Okay, we don't know where what this is, but of course this is nothing but minus of this function. So if we say this is our phi a, this function, so this phi a is equal to minus of psi a some, what is this, psi a phi a, whatever you understand this. So this sends unit disk to unit disk. We have proved twice in previous sessions, TS sessions, also in the classroom. But what is this phi a, which is given in the question? This is minus of that. So unit disk, when you apply minus to every number inside unit disk, where it goes? It is always lying in unit disk only. So applying by minus, you are just getting some reflection kind of thing. The plane reflection plane. No, no, not that. Multiplying by minus 1, you are rotating your disk 180 degree, right? You are rotating your disk 180 degree and it is going nowhere. Unit disk goes to unit disk, that is clear. So uh, this map sends unit disk to unit disk. We can prove that also, but we have 48 minutes maybe. We can prove this if we require. Right. So the first option says the function phi a maps boundary of D2 onto itself. Okay, I think we should check it. When modulus of z is equal to 1, what is modulus of phi of z is? Let's see. We are going to calculate modulus of phi z square, and then we will manipulate something. I hope we get our correct choices. Phi of a into z, this square is equal to phi of a into z into phi of a z bar. This is uh, some rule of complex analysis. You know that modulus is defined this way. Now, what is this? Z minus a divided by 1 minus a bar z into z bar minus a bar divided by 1 minus a into z bar. We multiply them. So what we get is modulus of z minus, okay, not like that. We have to write expression z into z bar into, sorry, plus a into a bar minus a into z bar minus a bar into z divided by, we directly write here something positive number, 1 minus a z bar modulus square. So this is positive number, that is clear. Now, what is a? A is having modulus less than or equal to 1, but modulus is positive. So this is mod z square plus mod a square minus So we get x z plus z bar. What is that? Uh, Real part of z, right? 2 into real part of z. So we write like this: 2 into real part of a bar z or a z bar. Okay, just like that, and divided by 1 minus a into z bar whole square. So when z bar is equal to so z modulus of z is 1, what happens? Sorry. I think this is not the way we should see. So phi of a, what we want to show that this is an in the interior part, what happens? If we see that it is an automorphism, what happens? So phi will be an open map because it is a holomorphic function. Because modulus of, okay, wait, we will start from here. Let me delete this because this is not, we are going to get anything. So we see from here, this is a Mobius transformation, right? This is holomorphic almost everywhere. This, so modulus of A is less than equal to exactly less than equal less than 1. This implies 1 minus A bar Z. This modulus, oh sorry, where's the problem? Phi A has singularity at Z is equal to 1 by A bar, which is if we check modulus of this, and modulus of z naught, which will be modulus of a or a bar, doesn't matter, both are modulus same. This is bigger than, exactly bigger than 1. This implies this. So the problem is not inside. This implies phi a, so this phi a is holomorphic in D. Now once it is holomorphic, it is open map, right? So open map sends interior points to interior points. So what happens to boundary? Most likely boundary is going to be boundary. If we show that IA sends open unit disk to open unit disk bijectivity, okay, then the boundary will be boundary. Fine. So we have to show phi A is an automorphism of open unit disk for this domain, how we show. So this is right. Phi of A applied to phi of minus A. Minus A is of course also lying inside unit disk if A is lying in unit disk. Okay. Uh, what happens if we apply Z here? It is just like the previous function here. Here it was self-inverse, but in the other case it is not because it is minus of phi A. The self-inverse doesn't work right here. The inverse will be phi of minus A. So that is what we are going to calculate. Is this the case? Let's calculate and see. In place of Z, so phi A of uh, minus A we are going to put, so Z plus A divided by uh, minus becomes plus A bar Z. Now phi A of the given value will be Z plus A by 1 plus A bar Z minus A by 1 minus A bar. In place of Z, we are going to write again Z plus A by 1 plus A bar Z. Right. Now we solve it and let's see what we get. Z plus A minus A minus mod A square Z divided by 1 plus A bar Z minus A bar Z minus mod A square. Now A minus A gets cancelled from numerator and from denominator. These two gets cancelled. What we get, we take Z common outside. We left with 1 plus, sorry, 1 minus mod A square. And in the denominator, we are getting 1 minus mod plus A square. But you see modulus of A is less than 1, so 1 minus modulus A square is positive number. From numerator and denominator, we get, because it is same number, we get we cancel them. We get only Z. So this is an identity function. So phi of A composed with phi of minus A, this is identity. What this says? This implies open unit disk, that part is open. It is bijectively going to open unit disk, use open mapping theorem, something result like that. The open thing goes to open unit disk and the boundary, the unit circle goes to unit circle. So from here we conclude phi A bijectively sends D to D. Bijectively means you understand automorphism. So interior, this goes to interior, boundary goes to boundary. Okay, so first option is correct. Now for the second option, what we have, for all Z inside this, phi of AZ is having modulus bigger than 1. And that is incorrect. We have just seen that but I don't think with that we require, because we had already Am I audible? Okay, assuming that I'm audible, let's continue. So this is incorrect. It sends unit disk to unit disk and boundary to boundary. Okay, we have not written why it sends unit disk, but we have seen this proof. Okay, okay. So let's see third part. For all z belonging to today, we have phi z. So okay, so this disk is open disk, and this option is correct. Open disk goes to open disk, or I think explicitly whenever required closed unit disk, d bar will be given. So no problem. We will understand that T is open unit disk. Del D will be the unit circle, which is boundary of open unit disk. So this is correct. Open disk goes to open disk, so it is less than 1. Okay, so for the fourth option, what we should do, AB was given by phi of A. We have just checked that inverse of phi A is phi of minus A. So this is the last option is correct, and this is incorrect. Just checked. Okay, so I think we have done this. Let's, if we have extra time, we will see what we'll see this part. Okay, again, because we have already done this, but we'll see if we get to recall our proof, because I'm not having it in my mind right now. We have 30 more minutes, so we can think about this. Now the very last question. Okay, so this is what we discussed. This is why we discussed earlier. This theorem, this is proved in the class. All the automorphisms of this form, where lambda mod lambda is 1, or this lambda into phi of alpha. phi of alpha is that z minus alpha divided by 1 minus alpha bar z, the function. So this is incorrect. This is also incorrect. This is correct. This is what the theorem is. Okay. I think this is directly from the classification of automorphism of unities. So I don't think to recall up the all of the proof. But we'll see last option. This is kind of interesting. This is actually also done in the class. If you remember this line, this one. When alpha is going to beta, f prime at alpha is bounded by 1 minus modulus of beta, which is a kind of f of alpha only, divided by 1 minus alpha is mod alpha square. This is what is written here. Modulus of in place of z, it is alpha, this is fz, this is beta, when alpha is going to beta. But they are same. This is done in the classroom, but let's see if we can do this or not. Even holomorphic function. Actually, this is a theorem in Schwarz lemma or Schwarz corollary of Schwarz lemma. Another some version of Schwarz lemma, Schwarz-Pick lemma. It is known by this way, but it directly follows from Schwarz lemma. What happened to this? F of z1 minus f of z2 divided by so there is some one minus fz1 bar into fz2. This modulus is bounded by z1 minus z2 by 1 minus z1 bar into z2. So these two are equivalent. We'll see at the end how these two are equivalent. But how's the proof for this? If we prove this is Schwarz-Pick lemma. In the star, Z1 tends to Z2 if we do this, or Z1 tends to Z2, right? In this way, what happens? So we manipulate a little bit. So this becomes f z1 minus f z2 divided by z1 minus z2. This is less than. So for the proof of this last statement, we have to prove this inside box inequality, because once it is proved, the letter is already seen when z1 tends to z2. We got this inequality at z2, and z2 is some general point. So we get the inequality, actual inequality. So we want to prove this box inside the box thing. Okay, how to do that? First, let's fix Z1 in T. Open Unity, fix something. So we define this map phi of this is not previous phi, so this is new phi I'm defining. Yeah, Z is equal to um, Z Z1 minus Z by 1 minus Z1 bar into Z. And so let's say another Mobius transformation like this, let's say which is psi of Z is equal to f of Z1 minus Z by 1 minus f of Z1 bar into Z. We have got two uh, Mobius transformations, right? And these, because f of Z1 as well as Z1, they are in unit disk. So these are automorphism of these are automorphism of automorphisms of D unit disk. So and also phi of Z1, this is going to 0. So what we can see here, phi inverse of 0 is Z1, and we apply f on it. So this is now fz1. If we apply psi on it, this is 0. So this implies psi composite f composite phi inverse uh, of 0 is equal to 0. So what we see here, this psi f phi inverse of z, this modulus is always less than or equal to modulus z. This is Schwarz lemma, using Schwarz lemma. Now what can we do here? So if in place of z we write psi of z, what happens? Psi of f of z, this modulus is less than or equal to phi of z. Now this is true for every z, so not worried about anything. Now what is phi of z? Let's say we place z is equal. We calculated z2. Let's say we are calculating at z2. What happens? Then phi of z2. What will be that? This will be phi of z2 will be z1 minus z2 divided by 1 minus z1 bar into z2 bar. So z2 is modulus. And on the left side, psi of z2, fz2. We put here psi of fz2 will be fz1 as it is minus, in place of z, what we are writing is fz2 by 1 minus fz1 bar into fz2. So we get this. This is what the trick was. Okay,